So today's topic is surface area of a quadric surface. So suppose this thingy is given by this equation, z is equal to f of, ugly handwriting, let me start over, z is equal to f of x and y. Okay, two variable function, so z is a function of x and y. How can we calculate the surface area? Only surface area we did last year was if it was rotated about the x-axis, y-axis like that. But now it's just any generic two variable function, any quadric surface. Okay. Now, tiny little, say we cut this tiny little area out, and thus we are going to call that ds. Okay. So if we take a little tiny rectangular cookie cutter, and then we cut that surface, and then whatever that little window that it makes is our ds. Okay. Now we need to find the formula for the ds, and this is a enlarged picture. So this is my ds, and this is my region. So I'm gonna label this. This thing is ds right here, capital S, as opposed to lowercase s, which is the arc length thingy. And this is my dA. You know what I'm saying? dA, of course, is this distance, which is dx, and this distance, which is dy. You know what I'm saying? So that's my dA. But ds, you see that it's potentially a little bit bigger because if it's tilted. So these two are not the same area. So we need to figure out what that ds is. So far with me? Okay, then I like to draw a couple of arrows or vectors. One vector I'm gonna draw from this point. This is like that. Good. So this is a given point, xy. And then that arrow extends out to that corner of that thingy. Okay, and then I'm gonna draw another arrow extending out to the other corner. Now, let me ask you this. Is this thingy, so this is vector A and vector B. You know what I'm saying? So this is vector A and this is vector B, which I have it here, vector A and vector B. Is this thingy a rectangle? dA is a rectangle because it's in our grid. Is my ds a rectangle? Is my first question. What do you say? The hint is this is tilted a little bit. So the shadow of this thingy, if the light is directly above, is a rectangle. Does that make this thing a rectangle? Kobe is shaking his head. So Kobe, what kind of shape is it then if it's not rectangle?
I'm not sure. I just know that you said those two aren't the same, the ds and the dA.
Oh.
So logically, it wouldn't be a rectangle. But I don't know.
Okay. Somebody share a brilliant insight. What shape is this possibly? I mean, it's a little curve, but it's infinitely small, so we can say it's flat. If it's flat, what kind of shape is it? Imagine there's some kind of flat surface and you're taking a rectangular cookie cutter at the bottom and you're cutting that thingy. What kind of shape do we end up with? Because we have to know what this beast looks like before we can slay it. Oh, ye children with no imagination, huh? This is a parallelogram, which could be rectangle, right? Rectangle is a parallelogram, but there's no, if it's distorted a little bit, but it's still flat. You know what I'm saying? So at least this is a parallelogram. Okay, then the next question is, how do you calculate the area of parallelogram?
the base times the height, and they have to be perpendicular to each other.
Yeah, okay. Do we have certain vector product that gives you exactly that?
Cross product?
Cross product gives you the area of parallelogram now, doesn't it? You want me to review that, or are we good now? Okay, I'm gonna draw it here because I already have two vectors here. So if I take a cross product, this is what A cross B looks like. Okay. And then that length of A cross B happens to be area of this parallelogram. You know what I'm saying? So cross product is perpendicular to both vectors that we are crossing. And this happens to be, where do I want to write it? I'm going to write it here. This happens to be AB sine theta right there, which is the magnitude of the cross product, isn't it? Do you remember AB and there's no, this is theta right here, but this is not necessarily 90 degrees because this is a parallelogram, not exactly a rectangle. You know what I'm saying? So all we have to do is find this vector A and vector B, and then we can cross them and it will take a magnitude, then we're done. You get it? Okay, then what is vector A? What does vector A look like? Let's think in terms of slopes. So if I move in x direction by 1, and this is purely in x direction, so my y movement is 0, correct? And then tell me what my z component should be. Slope, think slope. What is the slope in x direction?
dc dx. Partial derivative.
Yeah, this partial derivative. That makes sense to you? While x varies by 1, your z elevation changes that much. Who's confused about this one? Okay, then your vector b. Oh, now vector b is pretty trivial, right? There's no movement in x direction and there's only movement in y direction, but if I set that to 1, then that ratio should be your partial derivative with respect to y now, isn't it? So these are vector A and B. So far, so good. Actually, that I lied a little bit. This that's way too big because the side of the one is right. And then I'm going to multiply this one by dx to make it infinitesimal size and multiply this one by dy. How about that? Because we have to scale this vector so that your x direction, this length, at least this length down here is dx. And then we have some little bit of height, whatever that is according to that ratio. And I also want to make this little y direction size dy if I distribute this, and then that's the ratio of the elevation change. So far with me? Then my ds vector, oh, by the way, this ds has a direction, and that's a huge concept later, and that direction is perpendicular to this thing, upward, okay? And that happens to be vector A cross vector B. Good. Okay, let's take a cross product. And then I showed you how to take a cross product without writing the determinant, right? All you have to do is just imagine your I vector, J vector, and K vector here, right? And then we can think, oh yeah, determinant. Okay, so I vector, so is cross these out, this minus this, right? So we have negative partial z and partial f this way, so x, good. And j vector, this is a -1, so we have negative from the minor cofactor thing, and then this minus that. So we have partial z and then partial y. You with me? And then your k vector, of course, cross this out, so it's this and minus this, so we have 1. And then, of course, dx dy. With me? Say yes. Okay, and this vector ds, or many mathematicians call it n normal vector times ds. I mean, we'll deal with it later, and that becomes a huge thing later. But for now, this magnitude ds is just the magnitude of this vector, isn't it? So square root of this thing squared plus that thing is squared and plus 1, and that thing is of course squared, but we can take it outside. Whoa, that looks very familiar, right? Does that look like arc length formula last year? Yeah, we just have one more term, eh? Yeah, this is very analogous to the arc length formula, the lowercase ds. You know what I'm saying? So you can actually like memorize this and use it, but you should also know where these things come from. You with me? Okay, now we can put this to a use. So we have this. So we need to find the area, surface area of this paraboloid right here. That is lies, let's say under the plane z is equal to 9. So we're just cutting it off up to that height of z. Good. Okay, so let's do it. Okay, so what we do here is I'm gonna find the partial derivative separately, like I always do. Partial z, partial x, of course, is 2xa. And then partial z. Why is my handwriting so ugly today? And then partial z, partial y, of course, is 2y. So far, so good. Then we calculate ds. ds is square root of, this thing is squared, 4x squared, plus that thing is squared, 4y squared, plus 1, and then dx dy. You with me? And then now, does it trigger your memory? Do you want to evaluate it like this in Cartesian coordinate, or do you want to convert it into, say it?
Polar.
Polar, of course, right? Oh, this is very nice polar coordinate stuff, isn't it? So this will be, this thingy together is 4r squared plus 1. And then dx dy becomes r dr d theta. So this becomes nice use up. You know what I'm saying? I mean, whenever you see the circular region, why wouldn't you want to go polar? Good. You with me? So our surface area S is equal to the double integral of this thingy square root of 4r squared plus 1 r dr and d theta. And r will vary since this is 9 and this is 3 then. So 0 to 3. And theta will vary from 0 to 2 pi. You with me? Okay, so this is nice to use up. Do you want to do it in your head, or do you want to actually make a use up? Your choice. Somebody pick. Should we just integrate, or do you want to substitute u is equal to 4r squared plus 1?
We can just straight integrate. Straight
integrate it is. So 0 to 2 pi. This is 1/2 power, right? So this is how my brain thinks. Leave some enough space for r squared plus 1, and this is going to be 3/2 power. So far, so good? Say yes. So I put 2/3 for the time being. Now I differentiate this. So if I differentiate, that comes down and cancels this, but I have a chain rule to worry about. I'm going to pick up 8R dr. You know what I'm saying? So I'm missing that 8. So I need to adjust it by putting 1/8 right here. You see how that works out? With me? You don't have to do everything in your head. You can still adjust it like that. And then we simplify this fraction. So we have 1 over, what is it? 6, 4, 12. This is 1 over 12. Good. So we have 1 over 12. I missed something. I missed the bracket. And I don't have a lot of space. Okay. And then from 0 to 3. Good. Okay. Now, so I have, this thing is 1 over 12. Integral from 0 to 2 pi. And if I plug in 3, what do you have? Is it 37 altogether, right? So I have 37 to the 3/2 power. If I plug in 0, I have 1. Whatever that is, right? And then the theta. And if I integrate, this thing just gives me theta and 2 pi, correct? So which will cancel this. So pi over 6. Do we want to calculate? I don't want to. I mean, it's like, it doesn't even simplify. So how about that?